Takes 1 second. Okay, you're live. Okay, it's like a 30-second delay usually. Take 1 second. Perfect. Muted there. And yeah, so I run. So Matthias essentially later on, you will see that we'll switch the Q&A. Okay. All right. So let me start. It's 3 p.m. now. So thank everybody to come once again to the online SPICE-SPIN+X seminar series organized here by the Spin Phenomena Interdisciplinary Center in Mainz that I run together with Karen Eversossit, that is actually now in Duisburg, faculty professor there, and the Spin+X Collaborative Research Center led by Martin Schliemann and Burkhard Hillebrands in Kaiserslautern and Matthias Chloe in Mainz. This is a Zoom live seminar. That means that you please write your Q&A. You would see this the panelists, but not the other participants. But please write your Q&A or raise your hands, and I will give you the floor to ask questions to the speaker afterwards if you have a chance. The talks are always on Wednesdays, and please check the talks. At the moment, I'm not sure if the title has been updated for next week's talks, but it should be updated shortly. The speaker today is Kyung-Jin Lee. He's a chair professor at the Department of Physics at KAIST in Korea, and he's been a leader in the theoretical research spin-Spintronics, particularly spin-orbit coupling, and really resolving a lot of issues regarding this use spin currents and torques on magnetic systems, both ferromagnetics, also antiferromagnetics, and in a very thorough way. He's been professor now for quite a while, since 2005 in Korea, and before was a senior researcher at Samsung Advanced Institute of Technology. So he brings also a lot of expertise and connectivity to industry that brings a very interesting aspect of his research. So with this, I'm going to stop sharing, and I'm going to ask Kyung-Jin, please, to go ahead and share your slides and start your talk whenever you can.
Is it fine?
Change it to
okay.
remote, yeah.
Okay.
Perfect. Now it's perfect.
Okay.
Excellent.
Okay. Thanks very much for kind introduction, Harold. So I'm Kyung-Jin Lee from KAIST, and today I like talk about the spintronic research based on the ferrimagnetic materials. So I'll first give a brief introduction about our work, and the main point is that we used very actively the compensated ferromagnet because it has an interesting feature at angular momentum compensation point TA, where the net angular momentum vanishes while the net magnetic moment does not vanish. As a result, we expect there is antiferromagnetic-like dynamics, but we can use the magnetic field. The consequences of this feature of compensated ferromagnet is quite impressive, at least to my view. It realizes a very fast domainal motion at TA, and also the non-adiabaticity of the spin current for the domainal motion enhances, and Skyrmion Hall effect vanishes, and magnetic domainal can exhibit relativistic kinematics, and also the Magnum photon coupling largely increases at the angular momentum compensation point. So there is a lot of very good and extensive studies on the antiferromagnetic spintronics, and here are several very nice review articles on this subject. Actually, our original motivation was to study this antiferromagnetic spintronics, but we chose compensated ferromagnets instead of the antiferromagnet, and the reason was that my experimental collaborator Tero Ono from Kyoto University suggested me to establish a theory for the ferromagnet because it is much easier to de-experiment. That was the simple reason, because of the Zeeman coupling works in the ferromagnet. So we chose Leo's transmetal ferromagnet. As you know well, angular momentum S and magnetic moment M is connected through the gyromagnetic ratio gamma, and this gamma include the Landau factor G sub L here. And in this early TM ferromagnet, these longevity factors are different for two sublattices. For example, for cobalt, it's 22.2, whereas for gadolinium, it's 2.0. Because of these different longevity factors, when you calculate the net magnetic moment by summing up two antiferromagnetically coupled magnetic moment, it shows zero value at a temperature, which is called Tm, and that is the magnetic moment compensation point. And this Tm is different from another compensation point, that is Ta, called angular momentum compensation point. The reason of this difference is, of course, the difference of the longevity factor between these two sublattices. An interesting point actually appears at Ta. At this angular momentum compensation point, the spin dynamics is antiferromagnetic, but we have a finite net magnetic moment, and therefore Zeeman coupling works. So we can use magnetic field to set the magnetization direction in one direction, and also it is possible to create various magnetic textures, including the domain walls or magnetic skirmionts or bubbles and so on. Why this TA is important instead of the TM? The reason is that the dynamics of the state of the magnet is governed by angular momentum, not by the magnetic moment. We usually use this famous Landau-Lipschitz equation in terms of the magnetic moment m, but actually the original equation is this one, Heisenberg equation for the spin dynamics. And we just convert this S to m by through this longevity factor. If your materials, ferromagnet or antiferromagnet, consist of single type of element, then it doesn't matter. You can use both, okay? There is no difference. However, in compensated ferromagnet consisting of two different magnetic atoms, then we have to be careful. The dynamics is governed by this S, not by this M. And because in that case, we have to distinguish because they are different. So at TA, where the net angular momentum vanishes, but the net magnetic moment doesn't vanish, the spin dynamics of the ferromagnet is antiferromagnetic, but we can use a magnetic field. We first investigated the ferrimagnetic domain of motion driven by a magnetic field. So we derived equations of motion with two collective coordinates. One is domain position x that describes the translational motion of the domain wall. The other one is the domain angle phi that describes the rotational motion of the domain wall. Then we obtain these two equations of motion. And in our work, the most important term here is that this G value, that is gyrotropic coefficient, because this coefficient is proportional to net angular momentum. As a result, at TA, this net angular momentum, which is denoted by delta sub S, becomes 0. Then this G, gyrotropic coefficient, becomes 0. And therefore, we can drop these G-related terms in both equations. And here, this red F is the force. For example, if you apply the field, that can be an external magnetic field, or if you apply the spin-orbit torque, then it can be effective, a spin-orbit effective field. Then this force term actually affect only the X and therefore the translational motion without coupling with the dominant angle phi, which means that the X and phi are completely decoupled at TA. Then this force will be entirely used for generating the translational motion and without leaking to the to cause the rotational motion. From these equations of motion, we derived dominant speed in the precessional regime that is given by in this form, and also we derived the Walker breakdown field that is shown here. So at Tm, where m1 minus m2, that is the net magnetic moment, is 0. Of course, here we derive the domain wall by magnetic field, but the net m is 0, and therefore there is no motion. But one interesting point is that domain motion can change its direction when you change your temperature across this Tm. At Ta, more interesting thing can happen because at Ta, this delta S is 0, but M1 minus M2 is non-zero. So this term survives, and this delta S is that is in the denominator, which means that at Ta, this dominal motion speed may be maximized. And when you look at this Walker breakdown field, you can find that it is inversely proportional to the delta S, which means that at Ta, this Walker breakdown field goes to the infinity, meaning that there is no Walker breakdown. In other words, there is no rotational motion. So the collaborator Taro Ono's group carried out the experiment. The key person was Kyung-Jin Kim, who is now in the same department with mine, and they used iron cobalt gadolinium, and they fabricated this whole bar structure device, and they apply a static field B, and they inject the current here. Then the Worsted field create a magnetic domain at this side, but because of the static field, it moves toward this whole bar cross, and when it passes through this whole bar cross, then almost whole voltage changes abruptly in the time domain. So they can measure what is the time delay, arrival time of the domain from here to there, and they know the distance, and therefore they estimate the domain velocity as a function of the magnetic field and also as a function of the temperature. First, they determine the magnetic moment compensation point, Tm, using the almost whole voltage as a function of the field at various temperatures. At low temperature, hysteresis shows the clockwise variation. At high temperature, it's reversed. It's because at low temperature, layers moment is dominating over the transition metal magnetic moment, but at high temperature, transition metal moment is dominating over the layers magnetic moment. And at Ta, because net magnetic moment becomes 0, and therefore we need infinite field to switch the magnetization. So in experiment, it is not perfectly, not completely perfect, and therefore we still have some coercivity, but the coercivity increases a lot. So by plotting the coercivity as a function of the temperature, or by plotting the sign of this change of the whole resistance, at the same point, you observe abrupt change, okay? That gives the magnetic moment compensation temperature. And in this sample, it is found to be about 220 K. And they measured dominal velocity as a function of the magnetic field and also at various temperatures. The results are summarized here. So I just mentioned before, the Tm of the sample is about 220 K, but the maximum dominal velocity was obtained at around 310 K. And this experimental result is well explained by the theory. And according to the theory and numerical modeling, this dominal velocity maximized at Ta, where delta S is 0. And therefore, this maximum temperature, 310 K of this sample, is corresponding to the angular momentum compensation temperature. Okay, then we just add the current. The experimental setup and device is the same, but only difference is that we just add plus minus current. In that case, we obtain the two different dominal velocities at the same field, but with different current polarity. When we add up these two, then we can get only the field-dependent dominal velocity, but this analytical equation is exactly the same to what you have seen just before. And when we subtract these two velocities, then only the spin torque contributions remain. And this one consists of two terms. One comes from the adiabatic spin torque. The other one comes from the non-adiabatic spin torque. Here, P is the spin polarization of this sample, and beta is the non-adiabaticity of this sample. Let me first guess what happens for the VSTT, so the spin torque contribution to the domain velocity as a function of the temperature or as a function of the delta S. Here, I assume that the signs of spin polarization P and the non-adiabaticity beta do not change at TA. This is a reasonable assumption because the spin transport is dominated by the transition metal element, because the at the Fermi level 5D and the 6S electrons of the layers element is quite small. Their density of state is quite small. So adiabatic spin torque contribution has this kind of mathematical function. It looks like anti-symmetry Lorentzian function, and depending on the sign of P, it can show the black curve or red curve. And non-adiabatic spin torque contribution has the form of the symmetry Lorentzian, and depending on the sign of beta times P, it can be positive or negative. So by analyzing the experimental result and compare the sign of the symmetric part and anti-symmetric part, we can determine the sign, and also by fitting the result, we can determine the value of P and alpha and beta and so on. This is the experimental result. We vary the current, but the vertical axis is normalized by the current density, and you see that all the data points are collapsed into the single curve, which is good. And we can decompose this experimental result into symmetry Lorentzian and anti-symmetry Lorentzian. Then, when we compare this anti-symmetric Lorentzian part, we can find that spin polarization is positive. And that is reasonable because the spin polarization of cobalt ion is positive. And then we compare the sign of this symmetry Lorentzian part, and then we found that the sign of the beta P is negative. Because P is positive, it means that the beta is negative. And also, we can fit the experimental result using the equation that I have shown. Then we can get these three parameters. Alpha is about 0.003, and this is quite small. But this very small damping of this rare transition metal ferromagnet also observed in another set of experiment in this independent paper. So we are sure that the ferromagnet has a relatively low damping. And beta is negative, and also the value is quite large, 0.5. And the spin polarization is 0.1. This is a reasonable value. So concerning the beta, we had two questions. Why it is negative? And we searched the literature and found one theoretical paper from Garate. And he showed that the beta can be negative in systems with both hole-like and electron-like carriers. And we think that may be the reason of this negative beta. But the remaining question is, this beta is too large, okay? So we speculated that it may be due to the anti-ferromagnetic alignment of the spin moment in the system. So in this paper, we reported a theoretical study on the spin transport torque for the anti-ferromagnetic domain walls. We used the linear response theory in tight binding model. And here, two top panels is for the ferromagnetic domain wall, bottom panels for the anti-ferromagnetic domain wall, and left the adiabatic torque, and right is the non-adiabatic spin torque. So let me first explain the ferromagnetic domain wall. In all the cases, the horizontal axis is the domain wall width. So in case of the ferromagnetic domain wall, adiabatic torque, non-adiabatic torque, they do not show a meaningful change with varying the domain wall width. Only these different values were obtained from the different ferromagnets. And when we have these two values, we can calculate the effective beta term by simply divide the Cj value by the BJ value, and then we could get this almost constant value. But in case of the antiferromagnet, the result is quite different. The important part is here. The non-adiabatic spin torque rapidly increases as the domain wall width decreases. So very large non-adiabatic spin torque at shorter antiferromagnetic domain wall. Actually, this is caused by the spin stacking process. If the domain wall is very thick, then conduction electron spin can easily follow the magnetization profile. But if the domain wall width is shorter than the spin precession length, then it cannot follow domain wall profile, the change of the domain wall direction. And therefore, some quantum oscillation appears in the system that result in this negative dip in the spatial profile of non-adiabatic torque. And this is for the antiferromagnet. And when we focus on the thinnest domain wall case, you see that very pronounced negative peak here, meaning that we have strong spin mistracking process. And this previous result shows that the ferromagnetic domain wall case, there is no noticeable increase of the non-adiabatic torque, even down to the 6 domain wall width over d, is the lattice constant. But in antiferromagnet, even though it is quite long, it shows increase, and when it's short, then it becomes much larger, which means that spin mistracking process is much more dominant for the antiferromagnet than for the ferromagnet. We think this alternating exchange field is the reason of this enhanced spin mistracking process, and very similar conclusion for the spin orbit torque on single domain ferrimagnet was reported in this paper, which has been done by the Professor Hyun-Soo Yang of the National University of Singapore. Okay, so let me move on to the Skermion Hall effect. It is well known that for the ferromagnetic skyrmions, when you push your skyrmion into the longitudinal direction, but there is also the motion in the transverse direction, and this is very similar to the Hall effect, and therefore it is named as the Skermion Hall effect. So this Skermion Hall effect can be also explained by the Lorentz force. In case of the charge Hall effect, Q is the elementary charge, and this B is the external magnetic field. In case of the Skermion Hall effect, this Q is the topological charge, that is the Skermion number, and this B is a fictitious magnetic field, which is proportional to the net angular momentum. And therefore, in case of the antiferromagnet, this S net becomes 0, and therefore B0, and eventually Lorentz force is 0, and therefore there is no Skermion Hall effect. That was theoretically predicted in these two papers. So we wanted to check this vanishing Skermion Hall effect using compensated ferrimagnet. So we used gadolinium cobalt, iron cobalt platinum bilayer, and first we measured the DMI field using the micromagnetic droplet experiment, and found that it's about 60 millitesla, which is much larger than the dominant hard axis anisotropic field that is about 1 millitesla. And therefore, we expect that the magnetic bubble or skyrmions made in this sample may have a well-defined topological charge or skyrmion number Q. Then we measured field ribbon domain wall speed as a function of temperature to identify the angular momentum compensation temperature. In this case, the maximum domain wall velocity was obtained at around 280 K. So this sample, the angular momentum compensation point is 280 K. Then the Professor Ono's group fabricated this device, and this part includes the current line containing this half ring structure. So when they apply current here, the worsted field is concentrated downward or upward in this region, depending on the current polarity. And it can generate, because it is localized the outer plane field, it can generate magnetic bubble. So this is the mock image after current is injected. And you see that this part, there is a circle with a relatively bright contrast than the remaining part. So here we have a magnetic bubble upward. Then they injected the in-plane current, mainly through the platinum, to see how this bubble moves in the transverse direction. But unexpectedly, we could not observe isolated bubble motion. Instead, we obtained this result, meaning that this bubble is elongated in a specific direction. The reason of this elongation is that probably during the patterning process of this current line, we would make some damages on the sample, which generate a strong pinning potential for the magnetic bubble, and therefore it doesn't move. The isolated bubble cannot move, but it just elongated. But when we carried out the same experiment at the same temperature, but just reverse the direction of the all magnetization direction. So here, the dark part is down and bright part is up. Here, this part is down and all the other part is up. Then we still observe the bubble elongation, but what we found is that the angle of this elongation has a similar magnitude with opposite sign. So if this angle shows this kind of behavior, it may reflect the charge, the topological charge, because topological charge is the odd function of the order parameter. And therefore, when we reverse the magnetization direction, the sign of topological charge must reverse. So we thought that even though one end of this bubble is pinned by unwanted pinning potentials, but the other part can move. And in the other part, we have still half skyrmion, and therefore this half skyrmion has half topological charge, and therefore the elongation angle may have some information about this topological charge and also the skyrmion Hall angle. So we repeated the same experiment at the different temperatures. At high temperature, this angle is negative. At low temperature, this angle is positive, and in between, at the intermediate temperature, it is 0. So all the experimental results are summarized here. The blue dots are obtained for the magnetic up bubble, and red dots are obtained from magnetic down bubble. And it shows quite linear dependence with temperature. And in both cases, it crosses 0 value of the elongation angle at the same temperature. And this temperature is consistent with the angular momentum compensation temperature. So it actually proved that if the angular momentum is compensated, then the skyrmion effect must vanish. Okay, then let me move on to the next part of the relativistic kinematics. In this theory paper, we derived antiferromagnetic domainal speed driven by the spin-orbit torque. And we obtained this expression. Here, the important term here is the B sub D. That is the strength of the effective spin-orbit field, which is linearly proportional to the current density J. And for the ferromagnetic domainal, Andrabil et al. Derived this formulation, including the DMI contribution. So in this plot, I just plot these two equations using the same parameter set. So at the low current density, they are identical. At high current density, ferromagnetic domainal, the black one, shows saturation behavior because of the competition between DMI and spin-orbit torque-induced domainal tilting. On the other hand, the antiferromagnet domainal shows just linear increase as predicted by this theory because there is no domainal tilting in this case. And the similar phenomena was observed for the Nell-type spin-orbit torque in this paper. But when we carried out the numerical simulation based on atomistic spin dynamic model, we obtained these symbols. at low temperature and when the current density is small, then it follows this theoretical equation coming from this simple one quite well. However, when the dominant velocity becomes large, it starts to deviate from this theoretical equation and shows kind of a saturation. And this saturation can be understood by the relativistic correction, because the fundamental excitation of the magnetic system is the Magnum spin waves, and the spin waves equation of motion can be written in this form for the antiferromagnet that include second order derivative with time and also second order derivative with x, the space. This is quite similar to the Maxwell's equation, regardless of scalar potential or vector potential. In both cases, it contains second order space derivative and second order time derivative, and that gives the range factor, and also that gives the range invariance. And the consequences are no particle can exceed the speed of light, corresponding to the special relativity, and also there is the range contraction. In that case, the limiting velocity is, of course, the speed of light, and also there is time dilation and so on. In our case, the fundamental excitation is the Magnum. So when we use the same range factor, but instead of the speed of light, we have to use the maximum spin wave group velocity, then when we correct this term, we could explain our numerical result quite reasonably. The dotted line is this theoretical equation corrected by this range factor. And also we check that if there is indeed the range contraction by plotting the domainal width as a function of the domainal velocity. So when the domainal velocity increases, domainal width decreases, and these symbols, numerical results, are well reproduced by a theoretical curve that also include this range contraction equation. This theoretical prediction was experimentally proven by Jeffrey Beach's group at MIT. They have used bismuth-ig platinum bilayer. Unfortunately, this bismuth-ig is almost compensated, and it has very small damping. This very small damping is quite important to observe the relativity kinematics, because in the LLG equation, you know that the damping term contains the first order time derivative. So if that is very large or non-negligible, then the range invariance is broken. So this is their experimental result, and this line is the theoretical equation without relativistic correction. In that case, it shows the linear dependence with in-plane field, but the experimental result shows some deviation and some kind of saturation when the field is large. And in the theory and modeling, when we consider this relativistic correction, we could reasonably explain this saturation behavior. And from the measured values from the experiment, we can determine what is their maximum group velocity of this sample. That's about, it is about 5 kilometers per second. And then from experiment, we can extract the domainal width, and that is given by these black symbols as a function of the domainal velocity. And also we plot the numerical and analytical result that shows the domainal range contraction of the domainal due to the relativistic correction. Okay, the last part is for the Magnum photon coupling. This Magnum photon coupling may be important for quantum information process, because this cartoon shows various component for the quantum information processing as a function of the excitation frequency and also the occurrence time. The main candidate for quantum computing is nowadays the superconducting qubit. It is operated around gigahertz. One of the problem of this device is that its occurrence time is relatively short. So just like a hard disk drive or magnetic random access memory, we want to store this quantum information in some material system, which has the longer coherence time. So one very good candidate is the spin ensembles that, for example, ferromagnet, because it has the longer spin coherence length. The other important thing is that when we really want to do the practical and useful quantum computation, we have to transfer this quantum information to the photon. But the photon frequency is quite high in comparison to the excitation frequency of these devices. And therefore, if we can reduce this frequency gap, it would be very useful to realize the practical quantum information processing. In that point, the strong Magnum photon coupling at high excitation frequency would be very important. This Magnum photon coupling has been extensively studied in the field of the cavity spintronics. So the people usually put the EEG sample within the cavity, and then the magnon in EEG and the microwave photon in this cavity can be coupled. So for example, in this experimental result, this horizontal curve is the microwave photon dispersion. And this one is magnon dispersion that varies with the magnetic field. And if there is a coupling between magnon and photon, this crossing should be avoided. And the gap between these 2 points gives the strength of the magnon photon coupling. So the most experiment has been done with EEG. EEG is the ferrimagnet, but its property is very similar to the small magnetization ferromagnet, so it can be considered as a ferromagnet. So what we want you to know is that what happens when we use really the compensated ferrimagnet, which has the different TA and TM. So we derived the coupling efficiency that is given by the Magnum photon coupling strength divided by the excitation frequency, zeta, and we found this form. There are 2 important parameters. One is m sub L, that is the net magnetic moment. So because that it is located in the square root, which means that this efficiency is linearly proportional to the net magnetic moment. And this is quite reasonable because the coupling between the magnon and the microwave photon is nothing but the Zeeman coupling, and therefore the larger magnetic moment is better. But there is another term here. It includes delta S in the denominator, just like field-driven dimensional motion. So it means that when we make this delta S, net spin density to be 0, so at TA, then this term becomes maximized. And therefore, we may have maximized efficiency at TA. And we just plot this zeta value efficiency as a function of the delta S. And indeed, this zeta value efficiency maximized at TA, which is very far from the magnetic moment compensation point. So the reason of this maximized the Magnum photon coupling is that it is because of a concerted action between the antiferromagnetic diamonds that is related to the squeezing and finite Zeeman coupling at TA. So here we compare both excitation frequency of ferromagnet, antiferromagnet, and ferrimagnet, and also the Magnum photon coupling strength. The ferromagnet, it has large magnetization, and therefore coupling strength is relatively high. However, as we know well, the resonance frequency is relatively low. The antiferromagnet, red one, because of the antiferromagnetic coupling, the resonance frequency is high, but it has very small dynamic magnetization, and therefore its coupling strength is relatively low. But in case of the ferrimagnet, both can be very high, which means that we can realize strong Magnum photon coupling at high excitation frequency at the angular momentum compensation point of compensated ferrimagnet. Okay, so let me summarize my talk. We have studied the antiferromagnetic spin dynamics at the angular momentum compensation point in a ferromagnet, and we found that there is maximum field equilibrium domain speed because G-man energy is used only for the translational motion, not for the rotational motion. And we also find that the non-adiabatic spin torque enhances due to the pronounced spin mistracking process, and the relativistic domainal motion is realized, and Skirmion Hall effect vanishes by the same reason for this number one, and the Magnum photon coupling is also enhanced. So even though I do not discuss, you can observe the change in the spin wave handedness. There is right-handed and left-handed spin waves when you vary the temperature across the TA that was appeared in published in this paper. And all these results plus and challenges and opportunities of Ferrimagnetic Spintronics was published in this review article this year. So if you are interested, please visit this article. And as you have noticed, all these works has been done in very good collaboration with various people. I cannot write all the names, so only the faculty names here. Thank you very much for your attention.
Thank you very much for a very nice talk. Let me see. We start with the question Q&A now. Please raise your hand if you would like to ask a question directly. Anybody from the audience or write a question in your talk? I'm a little curious. Maybe I'll start. Okay, Igor. Let me give promote the panelist to Igor. Oh, and Gisela. So let me bring them up here to the so join in. So Igor, go ahead and ask your question. Can you unmute yourself and ask the question? Igor Sandalov. Okay. Then Gisela, can you go ahead and ask your question?
Hear me?
Yeah, go ahead. Yeah.
Thanks for this excellent, nice talk. I have a question concerning the material itself. So everyone who deals with these materials knows that the magnetic properties of rare earth 3D alloys depend strongly on the preparation condition, on the substrate, and also on the composition. And for spintronics or for any application, you have to control this. And also the current densities you shows are not so low that you cannot expect electromigration. This means that the material changes its properties during operation for a spintronic device at the end. Can you comment on this?
That's correct comment, and that is a challenge of the ferromagnet to be used as the practical spintronic device. And actually, I have asked this question to my collaborator who prepared the sample, Professor Tsukamoto. And his answer was that, you know, the ferromagnet was already commercialized in the magneto-optical recording, and there are many know-hows how to control the material properties. That is the answer that I can say.
But to be honest, these ferromagnets will be never used for magneto-optical recording. These are other materials as platinum, cobalt, chromium. So this the use of these alloys are 50 years old. So no one will use it anymore. And I think this is related to the problems with the material.
Oh, I see. But that is not my task. That is experimental.
He's still doing basic science. Thank God.
I'm free from that. I'm sorry.
Igor, go ahead. Maybe you can ask your question first, and then Matthias. We cannot hear you. Your microphone is off, or your. At least I cannot hear you. Can you check your input of your microphone, and maybe in the meantime, Matthias, go ahead. I can hear you now, Igor. Go ahead.
It's okay, yeah?
It's okay now.
Okay, thank you. My question is closer to your expertise. I mean that I'm interested in the origin of this coupling constant between magnons and photons. Is it coming from inverse Faraday effect, or?
Yeah, that's right.
That's right, yeah?
Yeah.
Okay, and then when the constant is increasing, then probably the two effects may be of importance. One is that actually simultaneously the same constant is responsible for the decay, right?
Which decay do you mean?
I mean that when you have the scattering of waves, one effect is just a gap between these two waves, yeah? So I mean that the photon branch and the spin wave branch repel each other, right? But another, in next orders, you should have increase of damping. And when damping is strong, then effect can be changed, and they are allowed to cross each other, and so on. It's one part of this question, and another part of this question is that actually when you calculate this inverse Faraday effect, usually epsilon is taken as a constant. But you consider frequency-dependent effect. And then the question is whether it's still does not depend on frequency.
Mm-hmm. I see. So thank you for a very nice comment. And all those terms are assumed to be constant here, K. So that is that comes from the Ampere's law and the Faraday's law. So yeah, I agree with you. Yeah, this value is not a constant, that it depends on the frequency and other things, also the damping. But we didn't do that because usually in the Eeg system, people just use the constant value for this K coupling constant.
Okay, so from experiment, you have to be sure that everything works pretty well. So you does not see any widths of these lines and so on.
I don't think I understand.
In spectrum.
This is experimental result for the Eeg.
Okay.
Yeah, it's quite reasonably large.
Okay.
Yeah.
So width of these lines is big, not big enough. Yeah. Okay. Thank you. That's the answer.
Thank you.
Thank you.
Matthias, go ahead.
Yeah, thank you. So a fantastic talk, really, really great and very educational. I have a question to I think the following slide, slide 30, the enhanced Magnum photon coupling at TA. One further, please. Just because I didn't quite understand, why should the coupling strength you get from your ferrimagnetic insulator at this compensation point, why is it stronger than that of a ferromagnet? I mean, I can clearly see why it is stronger than that of an antiferromagnet if it's just dipolar coupling, but why does it outperform the ferromagnet?
Yeah, so in the ferromagnet, we don't have this additional factor. In the antiferromagnetic system, we have this additional factor that comes from the squeezing of the Magnum mode.
Okay, so it is because it's much more linearly polarized than the more circular precession of the ferromagnet, which you assume as a sphere here. Is that?
You're right, but it is not based on the X and Y. You know, in the squeezing of the antiferromagnet, you have to add SX, SY, and here, and the other coordinate, the other things, right?
Okay, so it's a squeezing effect. And the other thing, which is the same slide, but maybe then it's also related, that is why is the slope of the resonance frequency versus magnetic field different for the ferrimagnetic insulator and the ferromagnet? Why
slow?
The slope. Why is it G equals 2 and it's just basically like a straight line, like the ferromagnet?
I'm sorry, would you please say again?
The slope. I mean, the ferrimagnetic insulator, the black line has the largest slope, right? So it changes much more with magnetic field than the antiferromagnet or the ferromagnet. And I guess in the antiferromagnet and the ferromagnet, it's just Zeeman G equals 2, I guess, that you're seeing here. And why is it different here for the ferrimagnetic insulator?
Oh, I didn't notice that. I have to look at my paper, the parameters.
Okay. Well, but, okay, so it's also something which is very, I mean, very interesting for applications, but which is not intuitive to me. Yeah. Okay, thank you very much.
Okay, Dong-Wook, would you like to ask a question?
Yes, thank you very much for the very interesting talk and nice overview. I also have a question about the material. So as far as I understand, most of the experiments on ferromagnets are performed on gadolinium, iron, cobalt, or something based on gadolinium. So my question is, are there other ferromagnets based on other rare earth metals like holmium or dysprosium?
So the most often used materials is, as you told, the gadolinium cobalt ion or gadolinium cobalt, and the other thing is that the terbium cobalt. And in the ferrimagnetic insulator case, Ig is the basic material, and people substitute the layers element such as the yttrium and TM and some other things.
I just wanted to ask this question because in gadolinium, the electronic configuration is quite close to the half shell. So that means that the orbital angular momentum is almost quenched. So the theory is relatively, I think, simple because we have only spin moments. But if we start to consider open shell F materials, then orbital angular momentum is really not quenched in F orbital elements. And I somehow expect that something interesting might happen in that case because of unquenched orbital angular momentum. So that's why I was asking if there are other ferrimagnetic elements with open shell F orbital elements.
Yeah, I agree with you. So actually, when we try to understand the experimental results, it is relatively easier for the gadolinium-based layers transition metal alloys, but it's much more difficult to understand the cobalt terbium result. In the cobalt terbium case, the terbium band is not it's far below the Fermi level, but not very far below the Fermi level. And there are some overlap with d orbitals and I think s orbitals too. So yeah, it shows sometimes very strange behavior, but I'm not sure it is because of this band structure problem or some other reason as the first question.
I see.
Raises. Yeah.
So I guess that still needs to be explored a bit further, in my understanding, if I understood correctly, right?
Yeah.
Yeah. Thank you.
Matthias, I think that's what
thanks, Kyung-Jin. Really exciting talk and lots of nice results. Can you just go back to the slide where we introduced the necessity for storage in quantum systems? So you had this introductory, yes, this one, exactly. So, for instance, for using superconducting qubits, what time storage do you actually require to help out? I mean, there's always obviously some minimum storage that is necessary, storage time that is necessary to help the architecture of some device. So is there?
I have no idea, but the longer is better because you can do more quantum task during that time.
And you say electronic spin ensembles are a good task. Of course, there are also these single spin qubits, not just the superconducting qubits. I mean, wouldn't they more naturally couple to like a spin ensemble?
I'm sorry, your voice is slightly.
Okay. Yeah. Okay. So I'll just try to speak up again. So. Yeah. Isn't it not so easy to couple superconducting qubit to electronic spin ensemble? Wouldn't it be easier to couple single spin qubit to spin ensemble?
There was a very recent PLA paper from Argon Lab. They demonstrate some coupling between the conducting qubit, but I'm not sure if it is a direct coupling or through the photon. Maybe through the photon.
We have to be through the photon because these guys are isolated. That's the whole point of this NV center.
Okay.
Yeah. Oh, absolutely. So I hope it's now better. Is the audio better?
Yeah.
Yeah.
Sorry about that. Okay, thanks a lot.
Yeah. Okay, so do we have any further questions? I don't see any more questions. Oh, sorry, just 1 second. Thank you very much. I have a question. Okay, sorry, 1 second. Lara said, let me find her. Laura. Yeah, let me bring her up. And then hopefully she's going to join in a second. And Laura, can you please ask your question? Unmute yourself and ask your question. Or do you have a microphone with you? If not, I can read the question. Go ahead.
Can you hear me?
Yeah, I can hear you.
Yeah. Hi. Thank you very much for your talk. So I had just kind of a basic question on this kind of intro sentence that is copied from intro to intro on these ferrimagnets, as which is saying that when the total angular momentum is zero, that necessarily implies it's anti-ferromagnetic dynamics. I mean, I understand why the LLG equation cannot be used anymore. And the way I understand the AF dynamics at TA is that the modes become linearly polarized, which you cannot have for ferromagnets. But I don't understand that whether by just saying L equals 0 necessarily implies, so maybe there's some kind of undergrad class I'm not remembering, but for me, it's more, I mean, you see it in the polarization of the mode, you see it when you solve the couple LLG equation. And if you are at the moment when the total angular momentum is 0, I think you basically fall back on the kind of sigma model AF dynamic equation. So this is the maths, but is there any just short explanation as to why L equals 0 means AF dynamics? Thank you very much.
What is L?
Sorry, the total angular momentum that you call S, maybe.
Okay. It's because the net, the overall spin dynamics is determined by the net angular momentum, not determined by the net magnetic moment, because the basic equation was derived from the angular momentum commutation relation between the angular momentum and the relevant Hamiltonian, right? And the other thing is that the LLG equation works quite well even for the antiferromagnet if you use the atomistic model, include both sublattices and so on. So it works well. And the sigma model captures the main part of this dynamics quite well, okay?
But yeah, I mean, again, I don't understand why it necessarily means it's anti-ferromagnetic dynamics that the total angular momentum is 0. I understand what you say about the on the slide, but for me, it's I mean.
So the important part of our work is that if there is a dominal tilting or not. So the fast dominal motion and vanishing common Hall effect are all related to if there is a dominal tilting or not. This dominal tilting is proportional to the net angular momentum, not net magnetic moment. And
yeah, no, I understand all this. Yeah, it's just this sentence, total angular momentum means AF dynamics. That for me is not. So Alexei is saying, does exchange field dependence on energy can also matter?
Don't think so.
Okay.
I mean, not for the point of view of that statement. I mean, I think Sally also, once you have antiferromagnetic dynamics, I mean, the equations of motion of the LRT equations do change quite a bit. You go from a massless equation to a massive equation because the systems are coupled. And this is what Kyung-Jin was showing, that you, at that moment, then, and also Helen Gomona is here, but maybe she's busy. Trying to get her to maybe comment because she knows everything about the phenomenology of antiferromagnets. But Laura, you work with her too, so you
I mean,
you can ask her directly.
I see that you cease to precess.
No.
But does that necessarily involve that it's an AF dynamics behavior? I do see.
Well, if you still have the exchange coupling between the systems, yes. Because then you will have, once you have dynamics, first of all, you have a magnetization, a small magnetization. So you will never have exactly 0 once you start doing the dynamics. And then that's necessarily the L vector and the other one will come in to couple together. As far as I understand, yeah. But that's a good fundamental question. I haven't really and then as Kyung-Jin was saying, the basic equations are derived from the angular momentum, not from the magnetization itself.
No, absolutely. No, this I completely understand, and I do see that at TA they're linearly polarized, which you definitely cannot have in a ferromagnet. So I mean, all this it makes sense. It's just this passage is okay. Thank you very much.
But Helen may be the one to contact.
I will. Yeah, I'm talking to her.
She's probably busy with Skype. Another one. I'm trying to bug it, but
I'll have a chat with her. Thanks.
Okay, great. Well, with this, I think there's no more questions from the audience. I wanted to thank greatly for the very wonderful talk that you've given us, and there was about 140 altogether in the audience. Now it's reduced a little bit because people after Q&A reduced the number. I'm going to stop here the streaming. So we have ended with the streaming, and remind everybody